the microphone. And so thank you for the invitation. And I must say I'm a bit stressed because dynamical system is not something I'm doing for every day. However, applied topology, with the field I'm working with, in a sense, has originated from the theory of dynamical systems. And I'll try to introduce to you applied and computational topology, but also try to stress as much as possible the connections to dynamical system, and as well as I can. So that's essentially the plan for today. Come on. That's too far. So we'll start. So when you look at the origin of applied and computational topology, there are essentially two paths where it originated. First of them was theory of dynamical systems, essentially looking at the relations of boundary dynamics to interior dynamics. And then if you want to do some sort of rigorous numerics, which is something I will introduce to you in a second, then you need also some topology. The second branch was computational biology, which I will only briefly mention later on. But let me start via main motivation going through the dynamical system. So we start by looking at the differential equation x prime equals f of x in Rn. Let phi of t x 0 will be a solution at the time t with the initial condition x0. So the set will be an invariant if it's actually mapped to itself. If I apply a map, I'll get the same set. And I've got another set, an isolating neighborhood, if the invariant part of the set is contained. Wait a second. Yeah, this is just a notation. So an invariant subset of n will be denoted by inv of n. It may be empty. That's just a piece of notation. And I will call n an isolating neighborhood if the invariant part is contained in the interior. So the invariant part don't touch the boundary of our set. So our set is isolating the invariant part from itself. So that's a small piece of basic notations. And here comes a little concept from topology, which is a concept of retraction. So they have two sets, A, which is a set containing B, and if I happen to have a continuous map from B to A, such that this map don't move points in A, so essentially the image of a point in A is the same point, so the map restricts to identity on the set A. And if this map is continuous, of course, then I will call A a retract of B. And then here's a piece of intuition. So if I have S1, which is a circle, and multiply it by an interval, what I will get is a cylinder. And then I can compress this cylinder across the fibers back to the circle. So in this case, a circle is a retract. Sometimes it's called a strong deformation retract of the cylinder. And that's a concept we will be using later to actually show that invariant parts of some sets are or are not empty. Right, so that's a piece of topology. And yeah, so I started by speaking about boundary dynamics versus interior dynamics. So let me introduce those two sets. So for a subset W, a subset of Rn, W0 will be just a collection of points that eventually leaves W. So all the points such that the trajectory at some time, and so some positive time, don't belong to W. So points that eventually leave W. By W minus, I will mean the points that leaves immediately. And what do I mean by that? Well, that for every positive time, if I look at the trajectory from 0 to that time, this trajectory is not entirely contained in W. So the points kind of leave immediately. W, so for instance, if that's my set W, and if I have a point over here, which trajectory is this red line, that point will belong to W0. However, if I take this point x0 at the boundary, then that's the point where the trajectory leaves immediately. So for any positive time, I'm inside my set W. Now, obviously, if I leave immediately, then eventually leave, and therefore we have this inclusion of W minus into W0. Okay. So that's a standard notation, and probably you will know that I'm kind of leading toward the Wazewski principle. So I want to define what the Wazewski set is. So essentially two conditions needs to be satisfied. Well, if I have a point in my Wazewski set, then if the trajectory of that point is containing the closure of my set that I want it to be contained in my set. Of course, if W is closed, that's kind of automatic. W is open, well, that's a condition that may be important. And the second condition for W to be a Wazewski set is that this W minus, so the collection of points that lives immediately, is closed in W0. So what do I mean by that? If I take a relative topology restricted to W0, then W minus will be closed. So for instance, if I take an interval from 1/2 to 1, half open, half closed, it is relatively close, for instance, in an open interval 0, 1, right? Because it's an intersection of a closed set in R with 0, 1, and hence it's relatively close. That's essentially the definition. And the Wazewski principle says that if W is a Wazewski set, then W minus is a deformation retract of W0. And if you look at the proof, it's actually a very nice construction, because the retraction really follows the flow lines of the dynamics. So the dynamics is telling you how to retract things. And that's kind of, in my opinion, one of the first principles of topology that can be useful in dynamical systems. How they can be used? Well, so let's think about the following setup. So let N be a compact isolating neighborhood. So it means that the invariant part of the set N is contained in the interior of N. And moreover, I assume that N is a Wazewski set. And it's quite straightforward to see that N minus, so the collection of points that lives immediately, they have to lie on the boundary of N, just by partial of N. And let's assume moreover, so topology is not telling you topology is telling you that something is not possible. So let's assume that N minus, so the set of points that lives immediately, is not a deformation retract of the whole set N. In this case, the set N0 cannot be the whole N, because we know from Wazewski that N0 is a deformation retract. So it has to be something considerably smaller. What does it mean? Well, it means that N contains the points that never leaves.
Could you make a picture?
Yes, of course. It's actually, I should have it. Oh, that's even a better picture. So we have a standard harmonic oscillation system, so contraction in this direction, expansion in that direction. And the whole set, so green and blue, is a Wazewski set. We can check it quite easily. There are no fixed points on the boundary. Everything flows either inside or outside. And the green set is an isolated, it's isolating with our unstable fixed point. So that's actually an illustration for the Conley index, but we can use the same. The exit set, maybe I will go back. It's exactly the same picture, it's just rotated 45 degrees. So we have contraction and expansion in this direction. So, and my set will be this square. I think that's my N. Right? And yes, and minus is somewhere inside, and minus are the points that immediately leave. So those are the points on that edge, on the lower left edge and upper right edge, where immediately leaves. And that's exactly the situation. So we have a square which is a compact set of homotopically equivalent to a point. We cannot retract it to something that has two connected components. So if you think about a continuous deformation, we will have to break the continuity at some point. So there is no retraction from a compact space, non-homotopic space to a space of 2 points, which is essentially the boundary. And therefore, from Wazewski, we know that there have to be the invariant set invariant subset of this set have to be non-empty. And indeed, we have this unstable fixed point. So that's what I'm trying to say over here. So that's exactly the situation when n minus is not a deformation vector of the whole set, and therefore I have a trajectory, at least one trajectory that stays in N forever. Right?
Maybe what is the definition of the invariant?
Say again?
Can you give the definition of the invariant?
Yes, so the definition of invariant. Oh my gosh, excuse me. Yes, so I'm speaking about forward invariant set. Let me just give a second to try to deal with technology. Whatever. So invariant, oh my gosh. Maybe this. Okay, let me do it on paper.
But it's not visible there.
It's not visible there, yes. It's not a good solution. Let me try to fix it. I can just type it in the chat, maybe. So invariant of the flow phi in the set X are all the points X in uppercase X such that goodness phi, if I map it from 0 to infinity, so again I'm speaking about positively invariant set of X is in uppercase X. But from the title, that's it. Okay. So I'm looking at in one direction, but of course you can look in both. Conceptually, there's no issue. Okay. Does it make sense? All right. So again, we are looking at we're kind of trying to infer. Come on. The moment I'll move to the next slide, I'll just continue talking. Yeah, I have to close it. Yes. So we get some information about the behavior of the dynamics inside our set, but by looking at the behavior on the boundary. And that may be a negative example. So you have just a flow going from left to right. Then the exit set will be just that part of the boundary over here. And of course, in this case, the whole thing is a deformation retraction. The flow is giving us the deformation retract. That was kind of important to realize that Wazewski principle is not event only if principle, it's only if principle. So for instance, if one of my trajectories stops over here in a fixed point, then the conclusion will still hold, but we will not be able to detect it via Wazewski, right? So if I have a fixed point somewhere here, the trajectory just stops and later on it continues, then I won't be able to see it. So it's not a silver bullet by any sense of imagination, but what I'm doing is a computational mathematics, and I want to be able to understand mathematics using a computer. So the question is, can we use Wazewski principle to do it? So there are a few essential steps that we need to make. First, represent our set U the computer, get any information about U minus, so the points that live in unity exactly, and that's actually not feasible in case of Wazewski. Check the existence of the retraction, and if we have a retraction, or if we don't have a retraction, especially if we don't have a retraction, then you can draw some conclusions about the invariant part of U being not empty.
It sounds easier to check that there isn't a retraction by some invariant.
Yes, absolutely.
To show that there isn't.
And that's exactly what I was trying to hint at the beginning. So topological invariants will tell you that two spaces are not isomorphic. But checking isomorphism much more involving process. And we will come back to this when we'll be speaking about topological invariance, if that makes sense, okay? The problem is, this set U minus, it's small set to approximate on a computer. It's not stable with respect to parameters of the dynamical system. And hence, Wazewski principle is not something that is, at least in a straightforward way, usable by doing some rigorous numerics. So the idea is we need to make U minus something larger. And here comes the idea of Conley, Charles Conley, and the idea of an index pair. So let me actually tell you what an index pair is. So I have an S will be my isolated invariant set, and I want to assess whether S, I want to provide an evidence that S may be not empty in some situations. And an isolated, an index pair will be a pair of sets, N and L. L is a subset of N. Of the following property. So we want N minus L to isolate our invariant set. And maybe let me go to this example which we already saw. So that's an index pair. So blue part is an L set. L from leaf. So that's a set where our flow is leaving our set N. The set N is the whole thing. And N minus L is the green part, right? And the green part, of course, is isolating my set S, which is the fixed point. And so what I am asking is that the invariant part of N minus L, so the green part, is in the interior. Wait a second, wrong way. What I'm asking is that the invariant part of N minus L isolates S, which is the invariant set. That's what it says. And there are two more conditions. The second condition is when I am in, so L is positively invariant in L. So if I have an initial condition in L, and the trajectory stays in my set L, N, it means that it stays in the set L. So the moment, every time I start from a blue set, I will don't go back to the green set. I can only live outside. Right? That's the condition number 2. And the condition number 3 is actually kind of a relaxation of this W minus in the Wazewski principle. So L is an exit set, as I mentioned. This condition is saying if the trajectory is outside N, it means that at some point, at some intermediate point, I have to pass by L. Right? And that's actually the case over here. So my set, then that's and the intermediate point I passed through the S set, through the exit set. Let me just show you this for okay, so that's the picture. We already discussed it. And what's the Conley index? Well, the homotopy Conley index is just a homotopy type of our set N after Conley. What would it be? So first of all, we can do it in 2 steps. First of all, I collapse, the left blue bar into a point, the right blue bar into a point, and then I need to make those points equal. So what I'm getting is something homotopy equivalent to a circle, to S1 in this case. And then the Conley theorem says that if the index is non-trivial, then the invariant part is not empty. Right? That's, in a sense, a generalization of Wazewski principle, but the set L is kind of fatter, so it's much more probable that I will be able to approximate it using a computer. However, there are a couple of problems. There is one problem with homotopy Conley index theory. So if you are working in computational topology, there is a standard result from 60s by Markov, which says that checking if a group is trivial is equivalent to a halt problem, which is a problem that essentially in general cannot be solved by a computer. So we cannot check if a group is trivial, and hence we cannot check if a homotopic group is trivial. We cannot check if phi1 is trivial. In general, again, there exist heuristics which works pretty well, but in general, we won't be able to do it for any possible input. That's the statement. However, we can have a recurring variant. Instead of looking at the homotopy type, we can look at homology or cohomology. So if I take a homology or cohomology, relative homology of the set N relative to the set L, if this is non-trivial, and we know from topology then the homotopy type will be non-trivial, and hence the common index will be non-trivial, and hence the invariant part will be non-zero. Homology and cohomology is computable if I have a discrete representation of my sets. And here we are at the birthplace of computational homology and cohomology. It really goes back to works of my supervisor, Marian Mrozek and Konstantin Mishaykov in the 90s. So we need to deal with this discrete representation of N and L. And what we are typically doing is to subdivide it into a collection of cubes. So we are taking our phase space and discover it with a collection of cubes. And I'll speak about that later. So there's a good reason why we are doing this. Because what we want to do is we want to do something rigorous in mathematical sense. And for that, we cannot use numbers, double precision numbers, as we have them on the computer. Because double precision numbers represented on the computer is just a finite subset of reals. There's absolutely no way you can do rigorous mathematics with that. So what we are doing instead is to use this concept which is called an interval arithmetic. And let me quickly explain to you what this is really all about. So the question we want to answer is, can we do any rigorous calculations? Rigorous in the sense of when the calculation finishes and shows something, it has the same power as mathematical proof written on the piece of paper. But can we do it? And the answer is yes. And the tool is an interval arithmetic. So I will be representing a real number x by an interval AB, such that x belongs to an interior of this interval, and moreover, A and B are numbers that can be represented on the computer. So there's a finite subset of numbers. Just take two neighboring numbers. If x sits in between, I just take this interval from A to B as a representation of x. And then what I can do is I can define basic arithmetic operations like addition, subtraction, multiplication, and division in the following way. So OP is just an operation. It can be one of those four basic arithmetic operations. So let's say that an interval AB plus an interval CD is a linear interval such that if I take X from AB and Y from CD, then the result ends up in this interval. So in practice, what we are doing, maybe I can tell you a little story on how computer works. So if I have a representable number A and representable number C, they're usually represented with 32 digits of precision. Let me not make it more precise. Then I can send it to my processor and compute the sum, A plus B. But the processor represents everything in 64 digits of precision. So I have additional precision. And even if I end up in between representable numbers, I can always take, in this case, the one which is smaller, the smallest representable number below A plus B, A plus C in this case. That will be the left point of my interval. So I'm taking A and C, I'm adding them. Not necessarily, there are almost never representable numbers. I'm taking just the largest representable number, which is smallest than this sum. I'm doing a symmetric thing on the right-hand side in order to get F. In any case, after this arithmetic operation, I will get an interval that for sure contains the real value of this addition. Right? So no matter which X from A and B and from A to B I take, no matter which Y from C to D I take, X plus Y will be in my resulting interval. So I am enclosing it. So that's how we can deal with basic arithmetic operations. And that's essentially all that computers can do. They can add and multiply. They do it very quickly. So all the elementary functions are actually computed using a finite prefix of the Taylor series. In rigorous numerics, we are not only using the Taylor series, we are also estimating from above the remainder term. So if I compute the prefix of the Taylor series, estimate from above the remainder term, then I have an interval from which, for instance, sine of pi over 2 lives, or whatever other elementary function you may think of. So I can rigorously enclose the real value. So we can approximate elementary functions, and this way we can actually start to make some mathematically rigorous statements using computers. For instance, if I have a function given as some sort of composition of elementary functions, f of x, and if I have 2 points a and b, and if I happen to check by a computer that the value of the function f at x is this interval, but it's kind of below 0 strictly, and the value of my function at b is strictly above 0, and with the help of the above property, I just proved that the function have a 0 in the interval ab, and that is a rigorous statement if I use this rigorous interval arithmetic. So indeed we can do something. Let's actually try to shift it onto the kind of flows or to theory of dynamical systems. So if I have a phase space and I divide it into these cubes, then if I'm able to solve a differential equation, I will estimate the error there, and I will briefly discuss it in a second how. Let's assume that for the moment that I can. But well, what I can do is I can compute an image of that cube. Well, it will be something nonlinear, connected. I can take a minimal collection of cubes that enclose that image. In this way, I get some outer approximation of the solution. That's what we are doing over here. So, for instance, if I have a candidate for an index pair, which is the set which we discussed already, then I can check the assumptions. I can check that there is no fixed point at the boundary, because if I happen to see that every cube from a boundary is mapped not to itself but to the interior or to the exterior, then I know that there is no invariant set touching the boundary. If I check that every cube from blue, from the red region, is actually mapped outside, and on the way it's crossing the blue region, then I can check the second property. And those properties can be checked, and if you are lucky, they will check out using this type of rigorous numerics. And therefore, I can prove using computer that that's an index pair, if I'm lucky, of course. And then, well, what is left is to compute homology or relative homology in this case of the whole set relative to the blue set. And if those are integer-based computations, so they're also rigorous. And if it happens that the homology or cohomology is non-trivial, then I know that the index is non-trivial, and then I know that the invariant part is non-trivial. And then I will be able to prove using the computer that there is something invariant in that set. Right? So I just wanted to mention very, very quickly, it's a big topic of how to approximate the solution of ordinary differential equations rigorously. So what we are doing, we are essentially using Taylor series methods. The simpler one is the Euler method, because again, we have the remainder term, which gives us an upper bound of the error we are making. As we overestimate, but we get a rigorous solution. So if we show something, then it's really over there mathematically. We can do it for ordinaries. I'm not aware of any rigorous methods to solve partial differential equations, which is a pain, because I know that people from Krakow would like to try to play with Navier-Stokes, but at the moment they cannot estimate the errors, as far as I know. So again, with this function f that maps cube to cubes, it will be just our flow obtained by a rigorous solution. For instance, using Euler method with rigorous bounds of the error term. By doing so, we can integrate the ordinary differential equations and actually say something about it. So the missing bit is, so we can actually define this flow, we can check the conditions, we can have a candidate for our index pair. What remains to do is to compute topological invariance, and for instance, homology or cohomology, and show me that this is non-trivial. If it is non-trivial, then we have an invariant set being non-empty. So I'll give you, if you don't mind, I'll give you a quick introduction to homology and cohomology. I will not do it for cubical complexes. I will do it for standard simplicial complexes. The definitions, that's a more standard exposition. I'll be happy to tell you more about cubes later on, but both of them are so-called homology theories. So you get an isomorphic homology groups, no matter if you use cubes or cubical subdivision of a certain set or simplicial subdivision. You end up with the same things, so that doesn't really matter. So let me start by basic data structure that we are using, which is an abstract simplicial complex. And it is essentially a finite set, the script K. It's a finite set of sets having the property that if I take any set from this collection, then every subset of this set has to belong to this collection. Okay, so let's take a look at example. So they have this set of sets contains of elements 1, 2, 3, 4, dubletons. I think there are 5 dubletons and 1 tripleton, and it actually satisfies this condition. So if I take a set and take any subset of it, it will be in this collection. But surprisingly, this abstract simplicial complex gives rise to so-called geometric realization, which is a simplicial complex that I have over here. So we have, those guys are vertices, they are zero-dimensional simplices. We have 5 edges, that's the first, second, third, fourth, and fifth edge. And we have one triangle. That's essentially a geometrical realization of this simplicial complex. Dimension of the simplex is a cardinality of the set -1, so vertices have dimension 0. Because there are no degrees of freedom, edges have dimension 1, because I have only 1 degree of freedom. If I'm sitting on the edge, triangles have dimension 2, etc., etc. So those are simplicial complexes. And there's certain relation between simplicial complexes, between simplices in different dimensions. So I should mention that every such a subset will be called a simplex. And that there is a relation between simplices in different dimensions, and this relation is given by so-called boundary operator, or the derivative, as we call it also in topology. And here's how it is defined. So first of all, I take a simplex consisting of vertices V0 to Vn. I order them in a certain way. Let me order them from V0 to Vn. It's actually related to a choice of orientation, which have something to do with the right-hand rule, if you like physical intuition. But then once I have an ordered collection of vertices, the boundary of that simplex will be just a sum of -1 to the power I, where I is the index on which we are summing, multiplied by a simplex in which the vertex Vi is taken out. For instance, if I have an edge from V0 to V1, then according to this formula, I should first of all take out the V0, and that will be with coefficient 1, and here it is. And then I'm taking out V1, and well, -1 to the power 1 is -1, and therefore I have V0, which is just that simplex. We've taken away V1 with coefficient -1. If I take a triangle V0, V1, V2, then first of all I'm taking away V0, and the I is equal 0, so -1 to 0 is 1. So I have V1, V2, which is that simplex over here. In the second term of summation, I'm taking V0, V2 with minus sign, and V0, V1 with the plus sign when V2 is taken out. Okay? So this is how we are relating the simplices of a different dimension. And now we need 2 or 3 more steps to define homology properly. So a chain of dimension I is just a free group generated by simplices of dimension I in my complex. And equivalently, we may say that that's a formal sum of simplices with certain coefficients. So for instance, if I have this polygonal line if I orient the simplices from A1 to A2, A2 to A3, A3 to A4, etc., then that's a chain. I can compute a boundary of a chain. Over here everything is nicely linear, so boundary of a chain is just this sum of a boundary, just applied to every simplex. What will happen for this chain if this is actually properly oriented? From left to right is that A2 will be present in the boundary of this edge and that edge with opposite signs, so it will cancel out. Likewise, A3, A4, and 5. The only elements that will not cancel out will be A1 and A6. And therefore, the boundary of this chain will be a sum of A1 minus A6, or maybe A1 plus A6. I think it will be A1 minus A6. So it really corresponds to a geometric boundary.
In this picture, where are the coefficients for the field?
Yes, so if I want, the coefficients should... Okay, so first of all, we are orienting simplices in a certain way, right? So I happen to misorient it. So for instance, this simplex is oriented from A2 to A1. Then in order to have it oriented properly, the coefficient will have to be -1 because it will swap the orientation. And then, what I want to do is, the orientation of the simplex multiplied by that coefficient over here have to give me, a polygonal line pointing in the same direction.
So the field here is the two set field, Z2.
So in this case, I'm speaking about integers. If we are speaking about Z2, then I don't care about orientation. Because, okay, so if we are speaking about Z2, then A2 will be in the boundary of this edge once, and in this edge twice. 1 plus 1 over Z2 is 0. So over Z2 is much easier. Over Z1 you really need to take care of plus or minus ones, okay? Any other questions? Maybe online as well? Please feel free to unmute yourself if that makes sense. Yes, please.
Why we don't see you? Something is complicated to do, but nobody sees you.
Integrated webcam.
You should open.
Can you see me right now? Good. I don't think I'm the most interesting person to see over here, so. Okay, any other questions online maybe? So those are chains, formal linear combinations of simplices. Yes? Basic algebraic topology. Yes, it's true, but in order to have something computable, you have to have something simple. I mean, otherwise it won't simply work. Okay, we need to list. So let's speak about cycles and boundaries. So a chain is a cycle, it gets empty boundary. So for instance, one-dimensional cycles, this green one and the red one, all the vertices will cancel out, and they will have empty boundary, and hence, the appropriate coefficients, or if we speak about Z2 coefficients with coefficients 1, this edge plus that edge plus this edge plus this edge, will be a cycle. It will have an empty boundary. Also, this will be a cycle. But there is something conceptually different about those two cycles, though. Right? So we kind of like this one, while this one seems to be trivial. And in order to actually quantify what the trivial means, let me define what's a boundary. So I have to move Jan a little bit away. Sorry, Jan. So a cycle, an I-dimensional cycle C is a boundary if there exists a chain in dimension 1 higher, I plus 1, such that the boundary of this chain it should be chain, sorry, there is a typo, it should be chain B, such that boundary of B is equal to our cycle. So let me go back to this situation. If I take, a sum of this triangle with appropriate coefficients, then in the boundary, this edge will cancel out, and the common boundary will be this cycle. So this cycle is a boundary. However, this cycle is not a boundary. Why is that? Well, because it surrounds the whole. That's an easy answer. But the real answer is, well, okay, boundary of what? So I'll have to take, probably, all the triangles around. But if I compute the common boundary, I'll get this cycle, but also the cycle going on the exterior. And it's kind of, if you think about it for a second, it's kind of easy to convince yourself that you cannot take a sum of triangles. such that the boundary will be the green cycle only. And hence, green is not a boundary, red is boundary. And we want to detect, the cycles that are not boundaries. But not only that, we also want to, so from the perspective of homology, the green cycle and the red cycles are the same. When we say they are homologous, because their difference is a boundary. It's a boundary of all the triangles which we have over here. And, that considerations are bringing us to definition of a homology group. So they take cycles, quotiented by the boundaries, I get the homology. So for instance, in that picture, the homology group in dimension 0 will be just the coefficient fields, let's say Z, because for every cycle is, every cycle can be, so a generator of this homology can be represented by just a point with a coefficient 1. Any other point can be connected with this point via line, and therefore they will be in the same homology class because they are different by a boundary. And it's essentially the consequence of the fact that this space is path connected. And we also have one generator in dimension 1 homology, and this generator is responsible for this hole in the middle. So that's what homology is doing. And I haven't been speaking about relative homology, but you can also compute it quite easily using basic linear algebra packages. Important message is we are using integer Z2 finite fields. They can be rigorously represented on the computer, so we can make those computations also mathematically rigorous way. So back in the 90s, the work by Marian Mozek and collaborators in the United States actually leads to the birth of computational homology, computational cohomology. At the same time, at the Duke University, the computational geometer Herbert Lorenz-Brunner was looking at the structure of proteins and considering a problem of the protein docking. That brings us to the second motivation of why applied and computational topology emerged at some point. So for some reason, there is this protein docking problem, and the biologists were looking for cycles which are almost close, but not quite close. And they realized that tools of geometry cannot give them the information about those cycles. Sorry? Docking problem of proteins. So if one protein is docking to another, so think about, it's not even a protein. If you think about a human cell, which have in the boundary of the cell, they have these channels through which things can go in and go out. And think about COVID virus, which is docking to that cell. This thing to which you are docking, and a part of COVID, there are two proteins, and if they match together, that's pretty bad, because the cell gets infected. So people, when they are designing drugs, they have vast collections of possible proteins, and they want to understand which of them can dock together. And that's a very, very serious, there are books, that's an industry by itself, quite useful in drug design, for instance. Because you want your drug to dock to a certain cell, for instance, in bacteria. Put something that kills the bacteria. So then considering this problem, yes, I will switch on the camera. It can be solved by one parameter homology to a sense, because what I can do is I can build a simplicial complex in different scales, but they quite quickly realize that there is no universal scale in which they see everything. So they really need to have a multi-scaling variant. And this is where they introduce so-called persistent homology. So I just have one slide. Again, that's a separated seminar if you want to go through the details. But let's think about the following situation. So I have a function. I'm looking at the sublevel sets of this function from minus infinity to a level A, and I'm moving A, up and down, and see how the sublevel set is changing. So for instance, it's a trivial situation of function from R to R, and sublevel set of the level I is just that bit, and this bit, and perhaps a little bit over here. And once I move A up, a new connected components in this sublevel set will emerge. Some of them will be joined together, and by computing zero-dimensional homology, which tells us about the connected components, I will be able to actually track the changes. That is essentially what persistent homology is doing. It's tracking the changes in the homology whilst certain one parameter is changing. Okay? Okay. We're done with the introduction. It took me a bit longer than I thought, but I'll just carry on. Now, topology originated from dynamics. Now I want to actually go the other way and try to use topology to understand dynamics and maybe to model dynamics. And I'll show you a few examples where those topology can be actually used. The first one came from my work with Thomas van Erst. So we are looking at the Cahn-Hiliard-Cook model. So again, I'm not the Dłotko who is dealing with PDEs, but that's essentially a standard Cahn-Hiliard equation, and we have the stochastic term, which is due to Cook. So what we are looking at, we are looking at the difference of the concentrations of two components. So for instance, this equation is used to model the following situation. So once you have a binary alloy, so an alloy consisting, for instance, of ferrium and chromium, well, we want to see how the relative densities of say ferrium and chromium is changing once we are applying certain processes. Of course, there's this random fluctuation term coming, to my understanding, essentially from the fact that we are dealing with quantum things. So there is certain uncertainty going on. What we can do is we can take this equation and solve it using spectral method, not rigorously, and we can get certain solution. For instance, those ones. So what we are looking at, we will solve it on a unit rectangle in R2, and depending on the initial proportion of masses of the first component and the second component, this one and that one, we're kind of getting different patterns. So, okay, we are solving it in time, and what is happening is, yes, I haven't done this computation, so I'll just tell you what I know. It was actually Thomas who did it. So we are varying the temperature. We are heating up the material, cooling it down, and do it many, many times. So essentially, the plot of the temperature is just a sinusoid. And once you do it a lot of times, you get the separation of phases. So atoms of one component group together and atoms of the second component group together. And looking at this concentration, so if that difference is zero, it means that locally at that point, we have 50% of one material, 50% of the second material. If it's getting towards -1, then we have only one material. If it's getting to +1, we have the other material. And that's essentially what this plot illustrates. And it actually visualizes the solution in time as the time progressed. Starting from one mixed material, we see the phase separated. So black means one material, white means the other material. What is interesting is that depends on the initial proportion of masses, we see different patterns. We see it with our eyes. The question is, can we use topology to quantify it in some way that those phases are different, so we get different patterns for 50-50, different patterns for 60-30% of proportion of masses.
This solution is not rigorous?
Is what?
It's not rigorous?
This is not, yes, it is not rigorous solution. So we actually, as a spectral method, so we use Fourier series. I don't remember the details, but essentially you express it as you look at the solution and the Fourier transform of the solution, and then there are methods that gives you the coefficients. That's approximation. Yes. So that's not rigorous because again we are dealing with PDE over here. Yes, so it's worth to mention it. So what we did essentially, maybe I'll just hand wave over here. We compute persistent homology. And, okay, well, there's another important thing to realize. So if I run the solver again, because of the stochastic term, I will get a bit different solutions. So essentially, I will get the same even for the same proportion of masses, because of the stochastic term, the patterns will be different. Black means concentration, higher concentration of one material, and white means higher concentration of the other material. So this relative. Yes, of course. We'll get much deeper into statistical physics in a second. Okay? But that is modeled by a partial differential equation. So what we are doing is we are discretizing time in which we are providing the solution, and for each time step we are computing persistent homology. And we do it for many solutions for the same proportion of masses. And then we kind of average the information we get. And we use this averaged information as a signature of a solution at that particular time. Something like a standard deviation is quite low. So what happens then, despite of the stochastic term, we get kind of a descriptor how, on average, the solution looks like if we integrate it until a time t for a fixed t. And the question is, can we actually do the reverse? So if you give me a solution of an equation, but you want to tell me what is the proportion of masses, given this initial computation I did, can I tell you what is the proportion of masses is? And based on having a numerical simulation, we determine that it is possible. Again, that's not a rigorous statement, but the topology of each phase at a given time tells us how far away we are into the space separation process. That's something practically important because we have different models for phase separations, Cahn-Hiliard-Cook being one of them. There are these 5 more models for the same phenomena, and they are real data. So people actually can measure those patterns for the different proportions of relative proportions of components. They see those patterns. So what we can do, we can validate models. We can check which models fits the data, which do not. Given experimental data, we can actually tell you how far away in the phase separation process the model is. Even using topology, this is not rigorous mathematically, but that's better that people with standard measures in statistical physics can do. So that's kind of where we can help. So what we are really doing is you are showing a snapshot of a solution, and I can tell you what is the proportion of masses, or I can tell you what is the time evolution from one mixed state in a non-rigorous way, but again something potentially useful. So we can detect different phases, we can detect phase transitions, and then we show you one of the examples out of many, which is the Ising model. It's the very standard model in statistical physics, where essentially you have a grid of points, and at every point you are measuring a spin. Spin can be up or spin can be down. Here's the Hamiltonian. So the second part is an influence of is responsible for an influence of external magnetic field. Typically we set up this guy to 0, so that do not count. And what happens in Hamiltonian? Well, you like the states where spins are iso-oriented, and if they are oriented in the positive way, that actually penalize the Hamiltonian. So if you want to get it to minimal energy, you want to have as many neighboring states in a grid oriented in the same way. That's good, that's good, that's bad, essentially. And that's a model proposed in 1920s by Ising, German statistical physicist, I would say. He proved that analytically that in one dimension you do not have a phase transition. Then in 40s they proved that in 2 dimensions that there is a phase transition. We don't know about dimension 3. In dimension 4 and higher, they're using something called a mean field theory in order to prove the phase transition for all the dimensions higher than 4. Again, the question is, can we spot any topological signatures of those phase transitions, regardless of dimension? So what we can do is, the simplest thing we can do is to just build a cubical complex. If the spin is positive, I said that the cube is present in the complex. If the spin is negative, I said that it is absent. I can, for instance, compute homology groups and the ranks of the homology groups, which we call Betti numbers. And see, and I can do it for many instances of the Ising model, and then see how it changes. So here it is. In dimension 2, we see, and that's for a finite size grid. So we see something that may eventually converge to discontinuous behavior if we increase our grid. And that's what happens typically in the thermodynamic limit. So statistical physicists are looking at the sizes of the grid that goes to infinity and see what happens. And that's actually what we are doing over here as well. So we see a spike, in zero dimensional. Okay. Yes. Let me say. So on the x-axis, we have a value of a temperature. So think about this as a value of a Hamiltonian. On the y-axis, you have a Betti number of the complex constructed in the way that if the spin is positive, I put a cube. If the spin is negative, I don't put anything. And I'm computing. Sorry? Oh, wait. Let me actually draw it. I'll do my best to annotate it this time.
Space for possible configuration.
Yes. So we start with some initial condition. Oh, it didn't work this time.
You can discuss clusters.
Yes. So for instance, if I have a configuration like this, then I build a cubical complex, which is in this case 3 by 2, and they can make an arbitrary decision. And if the spin is up, I put in the cell, and if the spin is down, I am leaving it empty. I'm leaving it empty. So there is no cube over there. So a cubical complex corresponding to this configuration. Okay. So I have this cubical complex, and I can compute homology group of this complex. Right. So in this case, there is one connection. Yes. Over here there are cubes instead of simplices.
Okay.
And if I look at the union of those cubes, then I can Can you hear me? Because for some
Yes, I can hear you again.
Yes, I can hear you.
For some reason I got disconnected. So let me share the screen again. And we are a bit further away. Okay. I think that the sound is gone. Hopefully it's back right now. So in dimension 3, where we don't have we do the same experiment in dimension 3, and over here we can see the zero-dimensional Betti number, which is the blue curve, one-dimensional, which is yellow, and two-dimensional, which is red curve. And we also see, okay, we are taking, yes, absolutely, and we are sampling this space. Well, we are sampling this space. Yes.
So you have for each state, some complex. And then
Yes.
you have
Yes.
no.
So we are
Numbers with some probability.
okay. So first of all, we actually evolve the dynamics until it stabilizes. The question is, what does it mean? It's not precisely defined, but we just start from an random initial condition, certain number of ups, certain number of downs that actually gives the Hamiltonian, and let the system evolve according to the Hamiltonian. At some point, it stabilizes. And in some local minimum, probably. And then we are taking this complex, this configuration, we are building a cubical complex based on this. So we are taking this equilibrium state, certain phases. We are building cubical complex in the way we discussed.
So special configuration.
Just a special. So we are sampling in Monte Carlo fashion, essentially.
You had some goal, which is of course, the way was going to stop, when to decide that you have arrived.
Yes.
And also you must decide how big you cut, let's say 2 dimensional time.
Absolutely. So first of all, the rule to stop is set up by statistical physicists, so it's absolutely not rigorous. Essentially, they're looking, if algorithm don't change anything for a few steps, for one step, the algorithm is deterministic. That evolves the dynamics of Hamilton. If there is no change from the previous step to the next step, they say we are in the equilibrium full stop.
Okay.
Don't ask me why. I won't be able to answer it. That's the first thing. About the size of the grid. So this plot is zero first and second Betti number for a certain size of the configuration. And then we repeat the experiment for larger and for larger and for larger. We look at the parameters of those curves. Then the discontinuities like this get sharper and sharper if we move to larger and larger configuration. And based on some statistical post-processing of those curves, they are able to get so-called critical exponents, which agrees with the standard results. So essentially, maybe let's look at two-dimensional configurations. That's for a certain size of a configuration. If I take it larger, that thing will converge to a Heaviside function, and that thing will converge to, I don't know, Dirac delta or something like that. Dirac delta. But you see this convergence only once the size of your grid is going to infinity, which of course, if you are doing computations on the computer, it's quite problematic. Okay. So this is what is happening over here. Let's see. I have like 10 minutes, I believe.
Now we have till 2:15 at least.
2:15? Okay. 1:45. Okay, good. So what I'm trying to say is, even though we are not making a rigorous computations over here, even if we take the simplest model in statistical physics, I mean, it's still challenging. So there are numerical evidence for phase transition. There are no mathematical evidence. So the existence of the phase transition has not been proven for Ising model in dimension 3. What we see in topology is that certain characteristics, for instance, Betti numbers, show something like a phase transition in a place where it exactly is supposed to be, with the same critical exponents. The point is, in dimension 1 and 2, there is a different technique of proving of the phase transition compared to higher dimensions. And topology kind of gives a unified view on that, which may be a hint for people who are actually proving something on that respect. So that's why, in my opinion, topology may be a universal language over here. By the way, it's not only about Ising model, there are different models in which we also see topology telling you something about phase transitions. So in this case, it's problematic because you have to go to the limit of. So you need to be able to prove that nothing is changing after a certain size, which kind of reminds me of a proof of four-color theorem. So if you look at the original proof of four-color theorem on the map by Apfel and Cahn from the 70s, they also prove that you only need to check certain conditions for the graphs of a certain size, because later, and there's an analytical proof that for larger graphs, nothing will change, and then they were able to bring it down into a finite computations. And if you can do something like this over here, then what you say can be true. But again, going to the limit is a problem for a computer in general. Okay, so let's see where we are. Yeah, so I did lie to you a little bit. The reason being, I told you that I put a cube where the spin is up, and I put an empty space instead of a cube. The spin is down. The problem is what is up and what is down is arbitrary to some sense. This is not canonical. So what we are doing in real research about that is we are using some sort of symmetrized version, which takes certain topological dualities into account to make sure that we get the same result regardless if we put a cube for a positive spin and empty space for a negative spin, or empty space for positive spin and cube for a negative spin. We still want to get the same thing, because those configurations are equivalent from the perspective of physics. We want to make topology agree on that. We have the tools to do it. Sure.
So you have two complexes. One is black and another is white.
Yes.
One is dual.
Essentially, we have a grid of points. In each grid element, we have a spin. Then I put the physical complex. When I'm using putting a physical complex, and for those which are out,
These are black.
those are black and the other are white. Yeah, that's as simple as that.
I just wanted to say that
Yes. Obviously, we have Alexander duality if we impose certain periodic conditions, which is, by the way, what they are doing anyhow. Okay. Any other questions, maybe from the audience online? Okay. So let me make a side note. So far we use topology to try to understand dynamics, and right now I want to move into topology to build models of the dynamics in certain situations. And in order to do this, I'll go to the side topic, which is another tool in computational topology, which is a ball mapper algorithm. That's my invention. And instead of giving you a rigorous definition, I'll just show you on picture how it works. So what we want to do is we want to understand a shape of a certain collection of points. Again, I'm a computational person. For me, finite collection of points is a typical input. Imagine this collection of points having a shape of the letter y is embedded in some nonlinear way in a 100-dimensional space. Can we still say that that's the shape of a letter y? Well, how we can do it, we'll use the following procedure. First of all, I'm taking a subset of points, which is an epsilon net. What's an epsilon net? Well, I'm taking a positive epsilon, and I'm picking any subset of points, which are the colored points in this case, having the property that for every black point, there is a colored point from my epsilon net at most epsilon away. Right? So as I'm kind of taking a uniform subset of those points. But what I just said was for every black point, there is a colored point for my epsilon net, at least at most epsilon away. This is equivalent to say if I put balls of radius epsilon centered in the colored point, then I will cover my whole point cloud. It's an equivalent way of saying this. And right now I want to have some low-dimensional representation of this point cloud. And I will give it to you in the form of an abstract graph. In order to tell you what an abstract graph is, I need to tell you what are the vertices and what are the edges of this graph. So the vertices will correspond to the centers of balls, and the edges will correspond to non-empty intersection of balls. What do I mean by that? Well, if two balls intersect and there are some points in the intersection, I'll put an edge between two vertices. So here's the graph, which will represent the point cloud. And now I have an exercise for you. Okay, so of course we are implementing stuff. If you want to use it, if you are playing with R, you can play with various point clouds. And here's an exercise for you. You know what it is? That's a lucky cat. If you go to Chinatown, it's typically waving to you. And here's the experiment setup. So I'm placing the lucky cat over here, and I'm taking my camera and taking a picture of the lucky cat, going around it from different angles. Right? I'm taking low resolution pictures, 128 by 128 grayscale pictures of lucky cat. And then every picture is just a matrix with values. And every entry I have either an integer between 0 and 255. And what I want to do is I want to linearize this matrix. So I want to create a vector where the first three elements are from here, the next three elements are from here, and the last elements are from here. So I create a vector, a point in 9-dimensional space that represent every picture. So in this case, if my pictures are 128 by 128 pixels, we are speaking about a point representing a picture living in 16,384 dimensional space. Question for you is, what is the shape of this collection of points in the 16,000 something dimensional space? And I gave you all the information to answer this question. So there are essentially two ways to answer this question. You can either figure it out, or you can download the software and check. In fact, we'll do both. Any guesses? Maybe from our guests online. So I'll give you a hint. So if you take a picture like this, we're starting in some point in high-dimensional space. And when I'm moving away from this point. But eventually, I'm coming back to something similar after I make 360 degrees. But I'm coming back from a different angle. So I'm not backtracking on the same path, which would be this. I'm coming from a different angle. So I already give you an answer, right? A circle, if we run the software, we'll get a circle in 16,000 dimensional space. So I'll try to train you in data science. There is something non-symmetric about this circle. Can you see it? Yes. Why? So in software, what you can do is you can click on every of those points, and it will tell you which picture it's coming from. So I made it easy. Okay, so long story short, those highly connected points is, the back of the cat, which is kind of uniform. Those points are much closer. If I move by a certain angle in the back of the cat, which don't have the is than in the front. So up in the picture we have the front of the cat, below in the picture we have the back of the cat. So this way you can do some basic data analysis using topology. The reason I was showing this bit is I really want to cover collection of points with balls, because later I want to construct symbolic dynamics based on this. Okay? And that's just the motivation. So let's move to the point.
Just say something about this.
Yes.
You also have some alcohol when to decide that to epsilon is different.
That's a fantastic question. Well, try and error. So either you can do multi-scale version, when you see how your graph is evolving, depending on an epsilon, or you try different epsilons and see what comes out. That's what you do in practice. There is no silver bullet. There is no procedure that tells you that you should use this epsilon for a simple reason. Your data set may have different features in different scales, and the method don't know which features you are interested in. And there is always some parameter to data analysis method. What we are trying to do in data science is to reduce the number of parameters to an absolute minimum, because maybe I should not say it when the meeting is recorded, but because users are typically stupid and they are tweaking parameters to prove their point. which is absolutely, which gives an absolute disaster from a scientific perspective. So we are trying to have as few parameters as possible. And of course, what you do, and again, in practice in data science, is you are doing a stability analysis. So we see this picture. Okay, let's try a few neighboring epsilons, a little lower and a little higher. We still see the picture. Yes, okay, that's probably it is over there. That's what you do in practice, because frankly, there are not many alternatives. We are working on alternatives, but there are not that many. Okay. So I want to put a little bit of criticism on some of the applications of mathematics, in particular in biological system. So ever since Sir Isaac Newton, what we are trying to do is we are trying to build models of various systems. In physics, it's quite easy because there are basic principles. So for instance, if you look at the gravity, the attraction thanks to gravity between two bodies is proportional to the product of masses and inverse proportional to the square of the distance between them. That's easy. If we look at biology, we don't understand the basic principles. And here's an so imagine I'm looking at this birth rate R. And the is kind of saturating the environment, which is set to 1 in this case. And I did work with some field biologists. Well, what typically they are doing is, well, we have a model, but they're going to the field and make measurements. Quite often they come back and say, for instance, in this model, your R is something between 3.8 and 4. And if they do this, if we look at the phase diagram, but not on the bifurcation diagram, then we are in this very chaotic phase. So if I, as a mathematician, want to make a predictions about this model, and if they tell me R is something between 3.8 and 4, and they will be very proud to get it that accurate, and still I cannot say anything because we are in this chaotic regime. So in practice, I cannot do predictions, even if I know precisely the model. Which is not the case, which is never the case. But in biology, with all the errors in the measurements and with our difficulties to understand the basic principles, we may be very unlucky and we may not be able to do predictions, even if we have exacting models. Okay, so what I'm trying to say is sometimes you really need to rely on data and data only. And the question is how to do it in a reasonable way, and that's what I want to discuss. So typical input which we are considering in this case, maybe for instance financial time series. So that's an S&P global time series. We have I think this is 2000. That's a .com crash. That's 2008 crash. That's 2013 crash. So that's the state of an economy during the last 30 years in the form of time series. And we want to understand the dynamics behind this time series. So there is presumably some dynamical system, some deterministic principles that are leading the economics, and we have some observation functions. For instance, this time series provided by some company in Manhattan, or we may look at the data from a brain activity. For instance, one project we are looking at right now is we want to predict attacks of epilepsy. We have, certain experimental time series coming from measurements. They're extremely noisy, and we want to understand the underlying dynamics. And the question is how? Well, obviously, in this crowd, I don't need to explain what the reconstruction is. Nevertheless, I'll kind of do it. So what we want to do is, so here's the picture. We have some deterministic dynamics, and we have some generic observation functions that is giving us a time series, one or higher dimensional. And from this time series, we want to reconstruct some sort of dynamics and hoping that it will be close to the real dynamics that we don't know that is driving our system. Okay, and of course, for this we'll use. So we have a time series. We want to turn the time series into a discrete trajectory using sliding window embedding. So that's a very standard thing. Let me just quickly run through it. So either we can have a connected sliding window in which we are taking the values of, in this case, 6 points. It give me a point in 6-dimensional space, and when I move my sliding window, I get the next point and the next point. And this way, I'm kind of sampling a trajectory in 6-dimensional space reconstruction. Of course, the parameter is the width of the window. That's, there are some heuristics on how to choose it. Window don't have to be connected. Still, from my observation, the reconstructions work. I'm not sure if that has any mathematical motivation. Though. Yes, we are getting there. It will be in the 2 slides, I guess. So what we are doing, this point is telling us, it's kind of giving us a local shape of the function. So for instance, if the spacing is the same, I can just, based on this point, I can make a partially linear approximation of our function. So it's a descriptor of a local shape of the function at a given point. And as you mentioned, of course, we are going to the Cahn theorem, which tells us, to my understanding, roughly that the dynamic, if we have a chaotic dynamical system in Rn, it can be reconstructed up to diffeomorphism by doing this type of sliding window embedding. Again, the practical problem is we don't know the parameters of the sliding window. We don't know whether the window should be this or that. And there are some estimates based on entropy of points. Or, there is something called false neighbor methods. Again, all heuristics. But if we,
his name is Hackens, so his name ends with an S.
Oh my gosh. Okay, sorry. Excuse me? Okay, Hackens. So I should remove the apostrophe.
There's no S, like no additional S.
Okay, sorry about that. I am dysorthographic, so sorry. Just Hackens. Yes, Florence Hackens from the Netherlands. So let's play with it. So what I did. Umaru? Yes. So what I did was to integrate the Lorentz system for quite a long time. So I'm just showing you a prefix of a trajectory because the whole trajectory will be very, very dense. And that's kind of a example I'm using to show some things. But if we take Lorentz system is embedded in R3, we can take, say, x, y, z coordinates. So that's an x coordinate time series. If I just take x coordinate of the trajectory, that's y coordinate, that's z coordinate. Based on this, I can do the reconstruction. So that's a reconstruction into R3 based on the x, y coordinate, and z coordinates. You don't see, this butterfly attractor because of I think unstable fixed point on the z-axis coming from Lorentz. So that's not a generic observation function, but those two are giving us the attractor pretty well. At least the prefix. The point is, if I'm dealing with a very long time series, I don't want to pretend to know the underlying dynamics. In fact, I don't want to make any assumptions. What I want to do is try to reconstruct this dynamics using Cahn-Hiliard-Cook's theorem without imposing any model, without imposing any parameters of this model, just by using sliding window embedding. Let's take a look at how we can recover some basic invariant sets, fixed points, or periodic orbits. And this is actually how this work started for me. So we are looking at time series from economics, and they had this. They believe something like economical cycle exists. So they wanted to see some periodic behavior in this time series, which is, once you look at the S&P. Where is it? Oh my gosh. SMP is nothing but periodic, so that's a long story. We did some detrending and etc. No periodic behavior show up, but that's another story. Instead of looking at the real-time series, let's look at something artificial. So periodic time series gives periodic orbits for the following reason. Sorry? Yes. So you have a periodic time series, then the signature of the point for this position of window will be almost the same as signature of the point for this position of window. So it's very much like with the cat, we're making a circle, and there's a sliding window embedding obtained from a sinus point cloud. What I want to do is I want to build a symbolic dynamics based on it. So I have an ideal periodic trajectory. That's what my unknown dynamical system is doing. What I have is some noisy sample of this periodic trajectory. I don't, not only I have points, I also know in which order they appear in the point cloud, right? Because I had a trajectory, it was too hard to draw. What I want to do is I want to do something very similar to the ball mapper. So I'm building in my epsilon net on that thing. Then I'm looking at the Voronoi cells of every point. What's a Voronoi cell? It's a subset of my point cloud. A Voronoi cell of point A is a subset of my point cloud for which the point A is the closest one. Likewise for BCM. So I subdivide my point cloud into those four symbols. And if I have my trajectory going clockwise, then I expect, seeing a lot of points with label A, followed by a lot of points with label D, then B, and then C, and then over and over again. If I kind of simplify it, I'm seeing this type of periodic symbolic dynamics over here. With the matrix which tells me which symbol is reachable from which symbol. I think it's called a transition matrix in this case. So I can reconstruct this periodic dynamics. I can try it on some data for which I know that they are periodic. So for instance, you can look at the temperature data from any city. In this case, we are looking at Melbourne, Australia, throughout 9 years. You use spectral method. And what we want to show, what we want to see is that the year has essentially 365 days. If you use spectral methods for this, so essentially Fourier analysis, it's quite off. If you actually look at something like a Poincaré map, so how long it takes me to return to the same symbol, I'm getting an estimate which is quite close to 365 days. That's a daily time series. So we really see that this variability. And again, even the simple method is kind of beating the state-of-the-art Fourier analysis, which is, in my opinion, a nice addition. But we can take it much farther. So what happens if I measure some device which is turning but in a different speeds? So it may be turning slowly and then speed up and then slow down a little bit and then slow down even further. That's a typical problem for Fourier analysis. But if we do topological methods, we'll get this type of dynamics where we are turning in one trajectory and then we are moving to another one and then we are moving to the third periodic orbit, and we can see it. So if you do a 100-dimensional embedding, you see different cycles on the different region of the space and kind of transitioning between them. Okay. We can also take a sine function which is composed with slowly growing function f. So a sine for which it's not the amplitude, but the phase is kind of increasing, the speed is increasing constantly. What is happening over here, we have a periodic trajectory going on a cylinder, and using this method you can actually see a cylinder. So I can actually show you the animation. So that's exactly the same cylinder embedded in 100-dimensional space. Oops, you can see that it's actually empty, and the coloring is telling you the time evolution. So you start from red and go through yellow all the way to blue, and it's actually wrapping around a cylinder. And that's what you can get from a reconstruction. Different other phenomena which are difficult for standard analysis, for instance, damping effect. What is happening is you have a periodic trajectory that is converging into a fixed point. So that's essentially what's happening. Periodic trajectory converging to a fixed point. And I'm out of time, right? Can I go for another 3 minutes? Sorry about it. Okay, but let's go back to business. We have this Lorentz system integrated for many million steps, and for me, the whole purpose of building model is to make prediction. And so to understand if an epilepsy attack will happen, or we'll have another financial crash, and I want to do it based on this symbolic dynamics, which I'm kind of reconstructing based on the model. So that's a symbolic dynamic for this a few million steps of integration of Lorentz system. But some of the edges are used more often. Some of the transitions are used only once or twice. If we remove those very, very rare frequencies, we kind of start to see the structure of an attractor, where we have we can wrap around one fixed point or around the other. We can simplify it further by kind of grouping together the landmarks, and until we actually see almost the butterfly dynamics. But that's not the point. The point I want to make is I want to be able to make predictions about the further evolution of the system. The way I'm doing this is the following. So I'm looking at the trajectory. I'm looking at the symbols that the trajectory is passing in the past. And I'm taking lowercase n symbols that has been passed by the trajectory, and I want to predict the next uppercase n symbols. And of course, if I integrate Lorentz for much longer, this type of prediction probably won't be possible. But again, I do consider this situation in practical, because in practice, I always have a finite time series. Over here, I have very long, but also finite time series. And what I want to do is, if I passed through, let's say, 10 previous, based on the 10 previous symbols my trajectory has visited, I want to predict the next 1,000 symbols. That's pretty ambitious. The plot is telling me how many different possible future evaluations there are. So there are something like 175 different possible futures given this 10-point prefix, again, based on my data set. However, if I'm looking at the 50 symbols back, which I have visited, which my trajectory on that sample have visited, and I want to predict next 1,000 symbols, there are only 4 possible futures, and the first one is kind of much more probable than all the others. So based on what I'm trying to say over here is not that I am able to make a prediction on how the Lorentz system will evolve. That this is not possible. What I'm saying is there are essentially 2 things. Looking at the symbols in my past, even though if I know that my trajectory is in a big region, so I don't have a precise location, which is pretty bad for a chaotic system. Given that I know my past, it gives me this additional precision on the localizing myself. And if I have a finite, large but finite time series coming from the Lorentz equation, the reconstruction therein, I can make a prediction on the future behavior of a trajectory with all the machine learning type processing that is done. So I'm taking the first part of the trajectory and knowing that my trajectory visited the previous 50 points, I'm trying to make a prediction, trying to lift it for the second part of the trajectory. It still works reasonably well.
Something opposite to independence of constitutive.
Absolutely.
So what's called chaotic.
Yes, which is in my next slide. So that is precisely the chaotic effect. So if I don't have any information about the previous, say, 50 symbols that my trajectory have visited, but I only have a location of the initial condition. I change it a little bit. This is how far away I am moving from the real trajectory. So,
You have big knowledge about the past and you have
yes.
it doesn't help.
No, it won't help me in general. But what I see in the finite sample of this time series is that in a finite case, it's giving reasonably good prediction. Of course, if I take much longer, it will break immediately. But my point is, in practice for any physical system, even if it's chaotic, you only have a finite reading. And if you want to make predictions, doing this reconstruction, at least for Lorentz, gives a reasonable results, even for a chaotic system.
Felix is saying, let's say that your data series is a perfect coin flip, 50-50. Will not help.
Absolutely not. But that's a yes.
Okay. But there are also cases where this will not work.
No, it will not work for a stochastic system. Absolutely not. Lorentz is quite chaotic, but yes. So if we integrate it much farther, everything I'm saying over here about predictability will break. But for a finite subset, which is what I'm getting in practice, I'm saying that the predictions are possible.
But for Lorentz, maybe stable, but very short in some cases. So if we are already close to the point, if we are in the local state and knowledge of the past, then the whole behavior of the local state is the same. But it's local, then knowledge of the past says something if we are not so local, so close.
Yeah, that's exactly the statement.
Related with non-uniform. Knowledge of past can help because we don't know the state of the figures.
Yeah, that's the empirical observation that I have over here. I have absolutely no mathematical justification why, but that's an empirical observation based on the toy example, which is Lorentz system in this case. So what I'm trying to say is that we can use time delay embeddings for the system for which we don't know the dynamics, even if chaotic. And still, if we are able to do some predictions for Lorentz, maybe we are able to do some predictions for those systems. That's the main aim for what we are doing, because for any finite time series, we won't be able to precisely show that the Lyapunov exponent is this or that. We won't be able to say that this is a chaotic system. Never, ever. That's not possible. But what biologists want to do, what people in finance want to do, in many other fields, they want to predict what will happen next. That maybe we can do based on this mechanism. And that's all I'm saying in this case. Again, we are lacking theoretical motivation, and that's why I'm very happy that I was given a chance to speak in this seminar. And let's see. So, well, let me just wrap it up. Topology originated from dynamics. I believe topology can help understand dynamics and maybe to model the dynamics. And that's, what we are trying to do over here. I will be very happy to talk more later on. So maybe just to tell you in that field, right now we are looking at the finance data and epilepsy data. This epilepsy data are challenged by itself because they are very large. But we want to use similar types of methods to actually do some predictions, which may be useful for either medical doctors or people in finance, with higher preference to medical doctors. I hope my finance collaborators are not here. Okay, and yeah, that's all I have to say. So thank you very much for your time, and I will be very happy to talk more, and sorry about going over time.
Questions? People online? No questions? No, we have a question. We have a question.
I have a question. I don't know. Were there any cuts harmed in the preparation of the stock?
Oh my gosh. Can you say it again, please, slowly?
Were any cuts harmed in the preparation of the stock?
Anybody can help, please? Could you please type it on the chart?
Whether any cats were harmed during the preparation.
Say again?
It was joke about cats. You said.
Okay. No cats were harmed. It was just a sculpture.
Okay, they got lucky.
No, I'm also a cat person, so don't worry.
I understood the technique was about basically doing these balls and then giving a symbolic.
Yeah, every ball is a symbol, and then you see.
And then, because regarding addition of financial series, I've seen a very big literature about this. So I was wondering, this is a new technique. This was not.
So if you know about some literature about time delay embedding in finance, please show me. Because we did some basic search, we haven't found anything in this direction. So try to kind of reconstruct the dynamics, symbolic dynamics from empirical time series.
There's nobody tried to.
Well, that's a too large statement. I think we haven't found anybody who tried.
Okay, thank you very much. Next seminar, and then we'll discuss it in 2 weeks. Monday, following.
Yes.
Bye.
Thank you very much. Goodbye. We can stop the recording.